So I've taken the stuff that we were going to cover on Friday, I pared it down and combined it with this. So if you have the note printouts, you'll probably see some stuff from Friday, and then we'll switch over and do some stuff from today. So there was some redundancy in those two lectures, and so that'll be fine. We'll be able to get through it. And so we're going to be talking now. We're leaving the particle in a box behind. Yay! Okay, we're getting into another one-dimensional problem, but this is vibrational motion. So we're going to be talking about individual vibrational modes in a molecule, but there are 3n minus 6 of those. So the number of atoms in a molecule is n, and every atom can move in 3 directions, x, y, and z. So we have 3n total things a molecule can do, but 3 of those are translations. So we're not interested in those. They're not vibrations. And then 3 of those are rotations. They can go around the z-axis, x-axis, y-axis. So we're not interested in those. We're only interested in the vibrations of the molecule. So we subtract those 6 things out, and everything left is a vibration. So it's easy. If you know the number of atoms in any molecule, you know the number of vibrational modes it has. It's 3n minus 6. The only exception to that is if it's a linear molecule. We lose one of the rotations, and so it's 3n minus 5 for a linear molecule. So that's the only sort of correction to that. Otherwise, it's 3n minus 6 vibrations. So each one of those vibrations is a vibrational mode. So you can think of think of your body too. Like every motion in your body is like this little joint on the end. That's a vibrational mode, right? I can do that, and it's completely unrelated with what my leg does. Okay, so everything every vibration in a molecule is orthogonal to all the other vibrations. And so we can talk about them one at a time, like this, shaking your head, but a molecule is doing it all at the same time. So all of them are moving at the same time, and it's chaotic. But every one of those has its own frequency and its own force constant, its own reduced mass, and so each one of those vibrations is independent of all the others. So that also means each one of those has its own quantum number. So things just got crazy. Every molecule has 3n minus 6 vibrational quantum numbers. So our electron in a box, we had one quantum number that described that electron in the particle in a box. But now every one of the vibrations has a parabolic potential energy function, and it looks like this. So every one of those vibrations is using this harmonic oscillator potential energy. The deviation from its equilibrium position causes it to rise in energy. Why is that? Well, because it's typically related to the bonds and the angles in the molecule, and those are governed by the electrons. So there is an optimized geometry, and that's what we did in Gaussian. We optimized our geometries. If we move away from that optimized geometry, the energy goes up, and that's this vibrational potential. Now you might see that kx squared. If you were to see that r minus re as x, then that's just Hooke's law. That's the classical physics that you see with a mass on a spring or a pendulum being acted on by gravity. So this is harmonic oscillator motion that you studied when you were taking mechanics. So how we get all these different vibrational motions, we use the projection operator. So there's a lecture on that, which we'll get to. Okay. They have known symmetry, and those motions are called normal modes of vibration. The word normal is just like we had with the wave functions, so normalized wave functions that govern these vibrational motions. It is a little strange, I'll admit, that the potential energy function uses a classical model, a mass on a spring. That's Newtonian physics. You studied that when you studied Newtonian physics. So that sets up the parabolic potential energy. But then inside that parabola are wave functions, which is quantum physics. So it's a little combination of the two. We have the potential energy, which comes from classical physics, but then the quantized energy levels come from the wave functions. So if we zoom in here, we see this bottom few layers, and we see those wave functions. And notice how they're very similar to what we saw with the particle in a box. They are not the particle in a box wave functions, but they're similar shape, right? We have one that's symmetric around 0, one that's not. So this is even and odd, all the way up. So very similar to the particle in a box, even though it's not One of the things that's different is look at the potential energy function. For a particle in a box, we had L over 2 and minus L over 2. And our potential energy was 0 inside the box and went up to infinity at the ends. Okay. And so our wave function, when it got to the end of the box, was pinned absolutely to 0 because the potential energy went immediately to infinity. So there's no way the particle could be outside the box. It had to have infinite energy for it to escape the boundaries. Well, the harmonic oscillator, the box goes up smoothly. So the wave function kind of penetrates the walls, if you will. You see this little area here. It's kind of like the wave function is penetrating the wall because the wall doesn't go sharply up to infinity. This causes, also for the box, if you want to think of this parabolic curve, look at this. These are the boundaries of the box. And notice how the boundaries with each energy level go further and further out. What happened in the particle in a box, the boundaries were straight up. And so the energy went up with quantum number squared, n squared. So the spacing between the energy levels went up as n squared. Whereas in the vibrational potential, the box gets larger as it goes up. And so that causes the energy levels to come down a little bit. And if the energy levels come down a little bit, the harmonic oscillator motion is just perfect so that there's an equal spacing in the quantum states. And so there's an equal spacing between all of these energy levels. This is the energy equation right here, showing equal spacing. Now, because of our typesetting and so on, the V and the nu look very similar to each other. This is the vibrational frequency, the Greek character nu. And that's the vibrational frequency, okay? This is the English letter V. And that V is the quantum number. So we have a totally different system. It's not a particle in a box. It's a vibrational motion. So we have a different energy equation. This is the energy equation. So you had the particle in a box memorized, right? You could rattle it out. N squared, H squared over 8mL squared. You could write that out, put it on your note card and everything. You got it. That's a particle in a box. Now we're in vibration, different energy equation. And that's okay. Every quantum system has its own energy equation because it has different wave functions. You saw the Schrodinger equation, you get a different energy equation out. Okay. And so these are the quantum numbers. Another difference is the vibrational motion starts with V equals 0. For a particle in a box, the ground state was n equals 1. So we're dealing with vibrational motion. We use the quantum number V for vibration. That's easy to remember. So it starts at V equals 0. And then V equals 1, 2, 3, 4, and so on. Okay. Now the symmetry is just like the particle in a box. We have even for the ground state, odd, then even, and then odd. So that's very good. So our selection rules ought to be the same, and that's nice. So our delta n's for a particle in a box were plus or minus 1, 3, 5, 7, 9, and so on. For V in vibrational motion, because of the even and odd symmetry, our delta V's are going to be plus or minus 1, 3, 5, etc. And so light is odd, so we could go through this and show that our selection rules give us the same thing, that whenever we have two odds and an even, we're going to have a non-zero integral. Now that's the harmonic oscillator. Notice how if this were a diatomic molecule, let's say HCl, Cl bonded to H. You know, the parabola shows this vibrational motion of the hydrogen. The chlorine is so heavy it doesn't really move, so it's the hydrogen vibrating on the chlorine. Okay. Now, if it really vibrates a lot, maybe the hydrogen stretches more. It can stretch more than it compresses, because when it compresses, it's going to hit the chlorine. But if it stretches, the bond just gets weaker as it stretches. And so it starts to deviate from a harmonic potential. So it becomes not harmonic, and anharmonic means not harmonic. And so we have this area over here where the hydrogen is stretching so far from the chlorine, the bond is weakened, and it spends more time out there, and then it comes back. It's like almost lost, but then it comes back, and it's vibrating. If you stretch it far enough, the hydrogen leaves and then never comes back, and you have a bond breakage. So because we can break bonds, we have anharmonicity, not harmonic behavior. But down here at the bottom, look, there's very little anharmonic behavior down here at the bottom. So when you're around the ground state, first excited state, it's pretty classical. It follows the harmonic oscillator very well. And that's why Gaussian can use the harmonic oscillator frequencies and give us pretty good frequencies for a molecule, because everything is in the ground state going to the first excited state. But we start to get thermal excitation. If it's a big floppy molecule, we start to see anharmonicity in our spectrum. Okay, so here's what happens to the anharmonicity. The energy levels are not equally spaced with anharmonic energy levels. Okay, so here, this yellow, these are the equally spaced energy levels. And so let me just label them 0, 1, 2, 3. We'll go up to 4. And now let's label the anharmonic energy levels. 0, 1, 2, 3, 4. You can see there's a pretty big gap between 4 for the harmonic oscillator and 4 for the anharmonic potential. And it just gets worse. In fact, the energy levels go into where they converge. At this dissociation limit, essentially the energy levels touch. You can't tell the difference between them. And then this distance in energy, remember this is the potential energy over here. So the distance between the 0 and this limit to where it disassociates gives us this dissociation constant, or dissociation energy. And the 0 would be the energy starting from V equals 0. And then the E would be from the very bottom of the potential. And there's situations when we would use E, and there was other situations where we would use 0, and it's not anything we need to worry about right now. But there's a difference between DE and D0. Okay. So these are the harmonic oscillator energies with V and nu. Also, when never mind, we'll get to that in a minute. These are the frequencies. So this vibrational frequency, I mean, you may look at that energy equation and you say, I don't see mass in that equation. I don't see the length of the box or anything like that. I just see the vibrational frequency. Well, it's because that constant has other constants buried in it. So this vibrational frequency is given here, where we have mass in the denominator. So just like the particle in a box, if I increase the mass of the system, the vibrational frequencies drop. So heavy atoms have a lower vibrational frequency than light atoms. So I'm familiar with the CH stretch from, you probably know that too, from the organic, little section of organic where you had spectroscopy and you're looking at FTIR. You should have in your head the CH stretch is in the 3000 region, 3000 wave numbers. And that's that tiny little H vibrating on the carbon atom. 3,000 wave numbers. Later in the semester, you're going to do the iodine vibrational spectrum. It's a diatomic, so you have iodine. What does it weigh? It's 127, I think. See over there, can you see that? 127. So the iodine, 127 compared to the hydrogen, that weighs 1. And its vibrational frequency drops from 3,000 with a CH stretch down to 217 for iodine. So increased mass, we have a drop in vibrational frequency. What's this K? This K is a force constant. So in this classical harmonic oscillator model, you have a spring and a mass. And so this is the tightness of that spring, how hard it is to pull on that spring. Now we know from springs, if you've played with springs before, it's harder to pull on a spring than it is to bend the spring. And so bending motions are easier or lower frequency. They have a smaller or lighter spring constant than a stretching motion. So the stretching motions are typically higher frequency than the bending motions. In the infrared spectrum, that fingerprint region, that's the bending motions of the light atoms and the stretching motions of the heavy atoms all on top of each other. And so that's why that part of the spectrum is so confusing. We can get out to the CH stretch, and there's really nothing happening around 3000 except CH is stretching, or maybe NHs or OHs. So the OH, NH, CH stretches, those are easy to identify and talk about in the infrared. But you get to the fingerprint region, it gets confusing. So this mass that I point out is called the reduced mass. And it's a way to reduce the masses of the molecule to those things that are moving. So if we have a diatomic, I said that the hydrogen's moving and the chlorine's not moving, but the chlorine is moving a little bit. So you have two masses, and you could reduce that to a single mass using this reduced mass formula. And then sometimes, to take into account the anharmonicity correction terms, we put these extra constants on there. And this is a good example of just taking a good energy equation like this that comes out of the Schrodinger equation, and you want to correct it. Well, one way to correct that is just to add higher order terms. What is a higher order term? Well, we've got the quantum number plus 1/2 here, and we know that we need to reduce it a little bit. So let's just put in a little fudge factor here, this anharmonicity constant, and let's subtract something, because as anharmonicity kicks in, the energy levels are going to get lower. So let's put in a small constant and then do it versus v squared. Okay, so it's going to go to 0 when we're at low v, but it's going to go up pretty quickly as we get to higher v's. And we just have this little constant, this anharmonicity constant that we put in. So that's what science does a lot of times. They'll take a good model, this is called the first approximation, and then they'll correct it. So they'll add a higher order term, maybe a squared term. You see this in your calibration curves, right? You want a nice linear calibration, but sometimes it starts to tail off. So you might add an x squared or concentration squared piece with a negative term so that you can model that little bit of curvature and maybe get a little bit more distance in your calibration curve. Well, all corrections can go too far. And so if you have really a lot of data points that you can fit in your spectrum, you might add back even a higher order term where it's cubic on the quantum number. And so this is related to the quantum number cubed. It's another little constant thrown in there, and this one adds it back. So we take the normal linear trend, we start to subtract some, but at higher quantum numbers we subtract too much, and so then we add back a cubic term. And so those are higher order correction terms. We will get into those a little bit in that iodine lab. So this is a bit of foreshadowing. We won't get to the cubic term, but we'll definitely need the squared term. Here's some molecular constants for diatomics. And here's like the force constant shown here. We're going to talk about the rotational constant later. Here's the dissociation constants. You guys are going to measure the ones in red. You're going to measure the distance, equilibrium distance of carbon monoxide in your lab. You're going to measure the vibrational frequency of iodine in your lab. You're going to measure the dissociation energy of iodine in your lab, and also I think you're going to get the force constant too. Okay. So you're going to be measuring all of these different constants for these diatomic molecules. We could go higher, but it just gets more complicated. So I think it's enough to teach you how to analyze the spectra of diatomic molecules, and then it's just more corrections and fiddling to do anything that's not a diatomic. But once you get the skills for a diatomic, you'll be able to do the others. So here's here's all the different equations for the force constants and so on. Let's look at the force constant in particular. This is also just a unit analysis too. Here's the energy equation. The quantum numbers have no units. We have the frequency and wave numbers here. And so in order to get the energy in joules, we use the speed of light in centimeters per second. So we'll see that in a second. And then the Planck's constant is joules times seconds. So the seconds cancel, the wave the wave numbers or centimeters cancel, and we're left with joules. Here's the unit analysis on the rotational constant. Notice anytime I have this little tilde on top, that's an indicator that my units are in wave numbers. Okay, so tilde equals wave numbers. And then here's the unit analysis of the vibrational frequency. Okay, so the one that's crazy, the mass is kilograms, but the one that's crazy is this one on top here, this force constant. So this one has some crazy units, and so let's look at those. So force constants, they're useful for describing relative bond lengths. And so we know that the fluorine molecule has a single bond, right? If you did the Lewis dot structure, you'd have all of those non-bonded pairs, but you'd have a single bond between the fluorine, and each one would have an octet. So you would easily identify that as having a single bond. And its force constant is 470 newtons per meter. So if I was wanting to stretch that bond, let's say that the bond didn't break in a meter, okay? It would take me 470 newtons to stretch that spring between that bond 1 meter, okay? Oxygen has a double bond. You're familiar with that. And look at the force constant. It's gone up. So again, a force constant is helpful for us to look at the strength of the bonds. And then nitrogen, a triple bond. Okay, it's got a force constant of almost twice the oxygen. But carbon monoxide, we're not sure. If you do the Lewis dot structure of carbon monoxide, if you try to make an octet, then there's some problems with it. If you try to reduce the formal charges, you end up with a double bond. And so this one is kind of confusing, but we could use that force constant to show that maybe it's like 2/3 of a triple bond, 1/3 of a double bond. There's another thing too, that the units are a little crazy. These are newtons per meter, which is fine. That's the MKS model. So these are two different systems of units. So unit systems. This is useful for you to know. So there's the MKS system, which you're familiar with. It's meter, so here meter, kilogram, second, MKS. Everybody see that? Yes. And then there's the CGS system. So centimeter, gram, second. And so when they were trying to decide how to standardize the units, they chose MKS. But there are still units that we use or phrases that we use that use the CGS system. So you may hear of a dynamometer, like if you're trying to test the amount of acceleration of a truck or a vehicle, you can measure the force, and the force is dynes. And so that word dyne for force is the same kind of idea as a Newton for force, except it's a different unit system. So we'll see sometimes the force constants given in dynes per centimeter. Okay, for force constant units, sometimes you have dynes per centimeter. And other times you have newtons per meter. So whenever you're looking up force constants in the literature to compare to your lab or your classwork, sometimes you'll see tables of dynes per centimeter. Sometimes you'll see tables for newtons per meter. And so here's how we convert newtons per meter over to dynes per centimeter. We break that newton into its constituent parts. Okay, then we start converting the kilograms to grams. Okay, we've got meters here, so we can get rid of those. We can go through and we can cancel all of these different units until we end up with the result of a dyne per centimeter. And the only thing that doesn't cancel is that 10 to the 3. Okay, so a newton per meter is a 10 to the 3 dyne per centimeter. I could also move that 10 to the 3 to the other side by saying it's 10 to the minus 3 if I divide both sides by 10 to the 3. And 10 to the minus 3 is a milli. So if you see the force constants given in dynes per centimeter, that's the same as millinewtons per meter. And then you can convert them to newtons per meter very easily. Let's talk about the transitions that we have. Remember, what was the fundamental, the quantum transitions for the particle in a box? If I said, write the quantum numbers for the fundamental, what would you have? 1 to 2. You've got that programmed into your memory. Well, that's ground state to first excited state. But the particle in the box, the ground state's n equals 1. But the fundamental is always ground state to first excited state. So now the fundamental is 0 to 1 because we started 0. So the fundamental transition, the most common, is from 0 to 1. Now I'll show it going backwards because originally all of our spectroscopy was done with emission. And so I just don't know why they do this, but it was the emission was 1 to 0. And so then when they showed the absorption, they just showed it with the arrow flipped. So it's 0 to 1. So just follow the arrow and it's 0 to 1. 0 is the initial state, 1 is the final state. I thought I went through the notes and changed all those, but obviously I haven't. So, but anyway, that's the old way of writing it out. Anyway, this is the transition frequency. So remember, whenever we have a transition, we can write out a transition equation. The energy at state 1 minus the energy at state 0. And so here's V equals 1. Here's V equals 0. Very easy energy equation. We pull HC nu out front, and we have 1 plus a half minus 0 plus a half. So the halves cancel, and we get HC nu times 1. And so this is the energy transition frequency equation. So it's just the peaks occur at the vibrational frequency. 1 to 2 is a hot band, 2 to 3 is a hot band, 3 to 4 is a hot band. All of those hot bands are just like what you learned in the particle in a box. And then anharmonicity allows all of the quantum states to occur. So all the transitions, plus or minus 1, 2, 3, and 4. So normally plus or minus 2 would be forbidden by symmetry. But that symmetry is based upon a perfect harmonic oscillator. If we let one side slip because we got a dissociation, now the symmetry is broken and we can have plus or minus 2 and plus or minus 4. And so these are called overtones, and they're stretches out in the near infrared region. Okay, so 0 to 2 is the first overtone. 0 to 3 is the second overtone. I'm going to go pretty quick. Okay. So let's go through the different types of samples that we have. Our infrared samples can be solid, liquid, or gas. But infrared is a very sensitive technique. So that just means that it's very efficient at absorbing infrared. So if we try to send infrared light through a sample, the sample can't be very thick because it's going to absorb all the light. Okay. Raman has trouble with colored samples because it uses visible lasers, and so a colored substance absorbs visible light. So if you send a green laser into something that absorbs the green, all that visible intensity is going to go into the molecule and catch on fire. So Raman with a laser a lot of times will catch your sample on fire. So you got to be careful with that, and especially dangerous. I worked at my last job in an explosives factory. Okay, and so I was testing Raman to see if it would be useful for testing explosives, getting vibrational spectroscopy of explosives. And I started with tiny little samples. So I had like one little speck of explosive, and I got the laser on there and I saw smoke, and that was a bad thing. If you had taken a big explosive sample, like a gram or something, charge, and stuck that laser on it, I would have blown my hands off, So start small. And then rotational structure, you can see in the gas phase, but you can't see it in the liquid phase because the molecules can't freely rotate, and certainly not in the solids. Okay, but it's really good to compare IR and Raman spectroscopy because both of them give vibrational information. So here's now the infrared absorption and Rayleigh scattering and Raman scattering, and here's from the first slide, the vibrational spacing. And so this little spacing down here is really close together, and that's the vibrational spacing. But we come in here with a visible laser, and we have a really, the laser has a huge energy. So that's why we draw that dashed line up there. And then this is Rayleigh scattering. We have no difference between the photons. It comes in, interacts with the sample, and comes off at a different angle, and it's elastic scattering. There's really no spectroscopic information there. So we're just not even interested in Rayleigh. We're interested in Raman. So this is our fundamental transition, 0 to 1, and the light comes in, interacts with the sample, but then the light comes out having lost some energy, and the molecule is now excited. And so the difference between these two is called the Raman shift. So this difference right here is the vibrational frequency. So we take the incident light and subtract out the scattered light, and the difference gives us the vibrational frequencies. Now, if we have some molecules that are already excited, we might get a blue shifted photon, and that would be the anti-Stokes shift. So the normal situation is the Stokes shift, the red shifted photon, but the anti-Stokes would happen if you had excited states. Raman is very good for probing like combustion plumes and so on. So a lot of our jet engine research, they wanted to see the completeness of combustion and so on. So they could send lasers through the combustion plume at the end, output of a jet engine, and they could do spectroscopy on it. Well, there you might have anti-Stokes Raman because you have molecules that are already excited thermally, and you could get some blue shifted photons coming out. So Raman's been very helpful in combustion research. Here's the FTIR of automobile exhaust, and we see some infrared absorptions and vibrational modes. And so we've labeled these with just the quantum numbers because the initial state, they were all in the ground state. Then they had excited states by these quantum numbers. And notice how our transition, our energies and also our transition dipole moment integrals get really complicated because now we have 3n minus 6 quantum numbers. This is the second vibrational state for CO2, this nu 2, excited here. And we see some rotational structure because this is in the gas phase. We see some water, and we see rotational structure. We see carbon monoxide with its rotational structure. We have CO2. This is this first vibrational state, or actually that's 3, 1, 2, 3. This is the third vibrational state for CO2 here. And those sharp lines are its rotational structure. Here we see some water that's condensed on the window. So we don't see the rotational structure for water there because it's condensed. And then we have these others, which we're going to talk about later. These are combination bands. And then we're missing a peak for CO2. It's Raman active only. So since CO2 is such a symmetric molecule, some modes are Raman active and other modes are vibrational or infrared active. So here are the two vibrations, the CO stretches. And we have the A1U mode here that is infrared active. It shows up at 2349 wave numbers. And then we have the A1G mode here, the symmetric stretch that's Raman active. It shows up at 1400 wave numbers. So now we're switching over to what was listed as the Monday notes. We're going to talk about the vibrational spectrometers. So how do we get this information? Well, first of all, we use the different parts of the electromagnetic spectrum. So we've talked about the visible spectrum, 400 to 700 nanometers, and this is to the red of that. So we're down in the lower energy area, the long wavelengths. We're going to talk about different types of spectrometers and different types of transitions. So here we are in the infrared region, which is redder than red. Okay, the near infrared is in 12,800 to 4,000 wave numbers, but most of the time our chemically interesting spectrometers are in the mid infrared. It's 400 to 4,000 wave numbers. There are different spectroscopic regions, and so here's just a quick chart that you would, I think I've asked some homework questions on this one, but we've got the UV from 190 to 400. the visible region 400 to 700, and then we're down here in the mid-infrared. And so our source is a hot ceramic glow bar. So we have a ceramic resistor. It will conduct a little bit of electricity, but it really heats up. If you force it to conduct electricity, it heats up. And that's great, because if it's hot, it emits light, just like the black body radiation curve. So if we can control the temperature of that ceramic, then we can control the amount of light it puts out, and it's a great infrared source. So it puts out a lot of energy in the infrared, and that's what we have in our spectrometers. And here's some essential equations for you. So we've got the frequency and wave numbers, and that's what you get if it's 1 over the wavelength in wave numbers. Any energy, if you have your energy in joules and you want to convert that to wave numbers, you divide by Planck's constant and the speed of light in centimeters per second. That should be per second, not meter. Okay. And then over here you have Planck's equation. The energy in joules is Planck's constant times the frequency in hertz. So we use frequency a couple of different ways. Well, say frequency, but if I say frequency or vibrational frequency, I'm typically talking about frequency in wave numbers. And so it would have that little tilde on top. So without the tilde, the Greek character nu is in hertz or per second. With the tilde, it's in wave numbers. And you guys know what's nu, C over lambda. And so that's a good way to convert from wavelength to frequency. Now here's all of your constants you can use in the lab. You can take them right here from the notes. You can look them up online yourself. But here's all the sig figs that you want to use in Excel. So for your lab experiments from this point forward and all of your experimental data, use all of the sig figs for your constants. That way you aren't having the, you're trying to measure something out to the 6th or 7th decimal place, and then you use Avogadro's number with only 4 sig figs. It doesn't make sense, right? So use all of them. There's 7 or 8 in all of the fundamental constants. So use them all. It's Excel. It can handle it. That way you're not messing up your precision by using the wrong constants. There are 2 types of spectrometers in general that we will have experience with. They're dispersive spectrometers. Like our little USB spectrometer, and also the one we use for the Raman is a dispersive spectrometer. The light comes in, it hits a diffraction grating and splits that light into a rainbow. And then we might have a diode array detector. So this diode array detector is kind of like a camera element. It's got pixels, light sensitive pixels all along this array, and it instantly gets a spectrum. Now those are very noisy detectors, because they crank up the sensitivity, so they basically give a lot of false signals because they're at room temperature, and so they say they're measuring light. You can put it in a completely dark room and it would still give you a signal. So it's just false photons. So what you do is you want to count a background. You shut everything off, don't let any light in, and say count for 3 seconds. And so it counts for 3 seconds and gives you that signal. And then you open the shutter, take a spectrum, and for 3 seconds, and you get all your peaks, but it's very noisy. And so you just subtract that noise, because those false signals are repeatable. So the same amount of false signal you get every 3 seconds, you could subtract from your regular spectrum. Okay. Now, resolution requires a more expensive diode array, or if we're using a slit in a detector, it requires a longer time because you have to scan slower and send the smaller slices of light through that slit. So resolution depends on the grating, on the slits, and on the smallness of the source image and the number of pixels in the diode array. Now, interferometric spectrometers are awesome. They're totally different. So here we have a source. Light goes through a beam splitter. So this is a 50-50 beam splitter. Do I have this revealing? No. So this beam splitter here sends 50% of the light up and lets 50% of the light through. And you may wonder, how does it do that? Well, they take a salt window and they just sputter a little bit of aluminum on it. And they measure how much goes through. So they sputter a little bit, and then they measure it, and they sputter a little bit more. And so then they know how long to sputter aluminum on this surface to make a 50-50 mirror. So That's their business, so they're really good at it. So they make a 50% beam splitter. So half the light goes up, half the light goes through. The light that goes through hits a moving mirror. So this mirror moves back and forth. And so then we have two different path lengths, and that creates an interferogram. So we send that interferogram through this instrument as a reference or a background, and then we put our sample in there and do the experiment again. And then we take I over I naught. So we can calculate transmittance using the transmittance is the sample spectrum over the background. And so you might have this infrared spectrum, look our background here, and then the sample spectrum comes along and it's got a missing amount of light there. And so that's where we get a drop in transmittance. So we take that ratio, and this is what our spectrum looks like. And then we take minus log of that, and we get an absorbance spectrum. And it looks like this. So that's what we see. So that's how we turn the interferometric measurement into an absorption spectrum. I'll write it over here, absorption. So this is our vibrational motion that we were talking about. I just grabbed this animated GIF off of the internet. It looks backwards to me. If I had a big atom, it would be on the left and a tiny little thing moving. But anyway, it's just showing you that this is our vibrational motion. And we use an attenuated total reflectance attachment. And so this little piece right here, it's a total reflectance. So 100% of the light is reflected. So how does it interact with the sample? Well, the top of that crystal is like this crazy little trampoline down here. Okay? And so it's bouncing electromagnetically. You know, the atoms aren't really moving, but the electric cloud above that diamond surface is bouncing like that. And if you have a molecule on the top, the vibrational modes can interact with that bouncing and steal some of the energy. And that's the attenuated part. Attenuation means to drop or lower. So it's attenuated total reflection. It's attenuated only where those vibrational modes are. And so we can get a spectrum out of this. It's great because there's zero sample prep. We put our powder on top, press a little anvil to make sure it's touching the trampoline, the diamond surface, and we send our light through the bottom of the diamond. We don't send it through the sample, just through the bottom of the diamond. And where the sample's touching that diamond, it can steal some vibrational energy out of that light, and we get a spectrum. This really made infrared spectroscopy super useful in the lab. You used to have to take your organic substance and mix it in with potassium bromide in a mortar and pestle and grind them together and put them in a little thing and press a pellet and then put the pellet in the infrared beam and send it through. If you put too much organic molecule in there, the peaks pegged the detector and they absorbed an infinite amount of light. So you couldn't get the peak center or anything like that. So then if you put too little in there, then your peaks were too small. So you're constantly making these pellets, and it's just terrible. It was a pain in the rear. You go to the ATR, you just drop your little powder on there, press it down, and you get a spectrum with zero sample prep. So this is what's happening in an infrared spectrum. Look at the spectrum on the left. It's sideways because here's the energy level diagram. So for this particular vibrational peak, this is a jump from V equals 0 to V equals 1, and all the others are still 0. So this is the fundamental for V equals 1. Does that make sense? And then you scan the spectrometer a little further. The arrows get longer. So we're scanning the spectrometer. Nothing happens, and then we get close to here. So scanning the spectrometer means you're making the light arrow longer as it goes through the sample. When it gets to this point, it's absorbed by vibrational mode number 1. Then you scan it a little further, nothing happens. And when you get to here, vibrational mode 2 absorbs, and 1 and 3 and 4 are still 0 there. And then you scan a little further, and now we get another peak where vibration 3 absorbs here. And then you keep scanning, and then finally vibration 4 absorbs. So you see this spectrum is all fundamentals. This is the fundamental for V1, this is the fundamental for V2, and so on. Does that make sense? Every peak in the infrared spectrum is a fundamental. Not like the particle in the box, right? The particle in the box, we only had one type of motion, the electron going up in excited states and so on. We had a lot of hot bands. We don't see any hot bands here. You might rarely see a hot band, okay? So when you look at an infrared spectrum, it's all fundamentals, okay? And it's just different vibrational motions in the same molecule. Okay, let's use Raman, and it's Raman, not Ramen. Okay, so don't mess that up in your reports. Put the A and not the E, okay? And this is the Raman laser from my graduate school days. It was so powerful, it hit a fellow who was walking through our lab, and he didn't see the infrared beam. It hit him on the side. It looked like cigarette burns. Went through his shirt and burned his skin. So it was a pretty powerful laser. He starts screaming, ah! We're like, what are you doing in here? You shouldn't be in here. We have all the safety features disabled when he walked through. Okay, now the modern Raman is handheld stuff, fiber optics. This is very similar to the one we had here. Okay. And so let's look at the Raman experiment here. So we're shooting visible light in. So this is the visible light coming in at 532 nanometers of light, a green laser, 18,000 wave numbers. So that's way beyond 4,000 wave numbers. That's 18,000 wave numbers. And then the scattered photons can come all the way back down to 0. That'd be Rayleigh scattering. Or if they hit this one, they spit out, this difference is fundamental number 1. This difference is fundamental number 2. This difference is fundamental number 3. So we get the same kind of spectrum. We see all the fundamentals when we take the difference between the incident light and the scattered light. So when we plot it versus Raman shift, it lines up with the vibrational spectrum from the infrared. So that's the Rayleigh and Raman and IR spectroscopy. And then just mechanically, we throw away most of the light. The Raman effect is very, very small. And so we have a lot of green light flowing around, very small number of photons coming out in the red and the yellow. And we'll finish up. I just want to show you this. So when we do a CH stretch in Raman shift, the light that comes out is around 633 nanometers. So it's still visible light. It can still go through glass. This is great. I can get infrared or vibrational information through glass. I can't do that in the infrared spectrometer because glass absorbs infrared light. And that'll be where we stop. Okay. So we're caught back up. See you next time.